Hi, in this lecture, I'm going to introduce more examples regarding how to solve linear equations using match current method and KVL, KCL, all these techniques being involved. So this will be circuit analysis part 3. Let's look at a circuit first. So this has a slightly different topology compared to the other circuits we have seen in the past. So this one has 3 meshes and one at the top. That's a difference. But there's no difference regarding how to solve it. You just use the same techniques. It's pretty simple. 30 ohms. This is 5 ohms. This is 80 volts. This is 26 volts. 26 ohms. This is 90 ohms. This is 8 ohms. First of all, so before we can list all the match current equations, linear equations, we need to draw the current, match current first. This is I1, and this is I2, and this is I3. And if we start traveling from here, going up for this mesh, we are going to see the minus 80 volts first, and then for the current, effective current flow through this 5 ohm resistor is I1 on the left to right, and I2 from right to left. Right? I2 is going here. So the effective current flow through this resistor will be I1 minus I2. So we're getting 5 ohms times I1 minus I2. And then the third one over here is I1 minus I3. Equals to 0. That's the first mesh. Minus 80 plus I1 minus I2 plus I1 minus I3. 26 ohms resistor. And now let's look at the mesh, the second mesh. You can start from anywhere, literally, but let's just get from here first. So you are seeing a plus sign if you follow the I2's direction. So that will be 30 ohms times I2. Actually, there's nothing else sharing this resistor, just I2 flowing through this resistor. And then plus 90, is that 9 or 90? 90 times I2 minus I3. Then this guy, 5 ohms, is I2 minus I1. Also equals to 0. Then the third one, we start from here, then it's 26 times I3 minus I1 and I3 minus I2. And the last one, which is 8 times I3 equals to 0. 3 equations. So what's the next step? Yeah, simplify all the equations. List all the coefficient of I1 on the left on the first column, and then I2, I3. Like that. And all the constants should go to the right-hand side. So the simplified equation looks like this. It's 31 I1 minus 5 I2 minus 26 I3 equals to 80. And then minus 5 I1 plus 125 I2 minus 90 I3 equals to 0. And minus 26 I1 minus 90 I2 plus 124 I3. This will be a nightmare if you do substitution. It takes time. You don't have to do that. If you like it, feel free to do that. But to save time, we would prefer use MATLAB to do this. So it's going to be AX equals to B, right? So A equals to the coefficient matrix, which is 31 minus 5, and minus 26, and then minus 5, 125, and minus 90. And here's minus 26, minus 90, and 124. And the constant matrix is 80, 0, 0. So in MATLAB, what you should do is, type A, right? Type A into a matrix, and type B into MATLAB as well as a matrix, and then just type X or I, doesn't matter, equals to inverse of A times B, and it's gonna show you that result. Okay, I won't do this again since I already showed you how to do it in the last lecture. So let's save some time so we can cover more examples, all the different types of circuit. I think that's more important. So now let's look at a different example. Let's label that example 1, and then so this is a circuit which contains a different component you haven't seen in the past. So something like this and plus minus is different from this one we have seen. I'll just label this guy as like 5 volts or something. But this is a voltage source, but this is dependent on a different voltage source. If I label this guy as 3V1, so you don't actually know what's the exact voltage value of this voltage source, but it is dependent on the other voltage source, which is V1. So this is called voltage controlled voltage source, because the voltage value of this guy is controlled by a voltage. So it's a voltage controlled voltage source. And this is a type of dependent source. Dependent source. Yeah, just let you know. But we don't need to worry about that. You just need to know this guy is 3V1, 3 times V1. What is V1? We don't know. We can solve it if we need to solve it. Doesn't matter. So let's look at a circuit which contains a dependent source over there. So that's a dependent source, plus minus. That's a tiny resistor, 1 ohm. This is 10 volts. This is 5 ohms. This is 25 volts. That's a standard voltage source. And this is 2 ohms. This is 3 ohms. This is minus 3 V1. And what is V1? So the voltage drop across this resistor is called V1. And this is 14 ohms. So how do you list these linear equations for this guy? It's actually pretty simple. Just follow all these mesh current method rules, and eventually just get one more variable. But you can find out V1 from here, use the current. Right? So it's literally no difference. So let's run this really quick. So if you see this, you're not nervous. Right? So if you start from here, so we're seeing a minus 25 plus 2 times I1 minus I2 plus 5 times I1 minus I3 plus 10 equals to 0. And the second one, start from here, then it is minus 3 V1, so it's actually 3 V1 plus 14 times I2, and come back. It's I2 minus, so 3 times I2 minus I3. And then the last one is I2 2 times I2 minus I1 equals to 0. And then the third mesh start from here. For example, that would be minus 10 plus 5 times I3 minus I1 plus 3 times I3 minus I2 and plus 1 times I3 equals to 0. But we have 4 variables, but only 3 equations. So the very last one is actually hiding here. How to find out that one? So that's a real voltage drop across the resistor, but we don't have a real current, the physical current flows through this right now. So I have to find out if the voltage drop is from here to here, then you can imagine the effective current is following that direction. Then it's actually following I3's direction. So you can use I3 minus I2 to get the effective current flow through that resistor. So these are all the equations you need to simplify. And you simplify, get all these currents lined up, and all the coefficient will be pretty easy to figure out. And then you type everything into MATLAB and solve it after that. Okay. I'm not going to do that, so I just want to show you more examples. This is the example 2. Okay, let's look at the other one. It's called, here's a new technique. It's called super mesh method. No fundamental difference, but just trying to simplify anything you can simplify. Super mesh. So if you have something like this, you can simplify it further. Just trying to reduce the workload slightly, okay? Because there's no real difference, right, between these two, the super mesh and regular mesh method. It's 40 volts. This is 2 ohms. This is 8 ohms. This is 6 ohms. This is 2 amps. It's a current source flowing up. This is 4 ohms. This is 20 volts. So whenever you see something like this, a current source bridging these two nodes, something like this, you can ignore it. You can ignore it and directly just starting from here to here without listing 3 equations, but only 2. Okay. So the reason of that is Vx is being cancelled. So what is Vx? Because you do not know what's the voltage over here. Because you cannot use a Ohm's law to, do I times R equals to voltage here. You actually don't know what's the voltage over here. So I have to assume it first. Keep in mind, I have to assume a Vx first. So Vx is the voltage at here, and which is also the voltage across this current source. Because here's ground, this is 0 volts. So Vx is the voltage at this node, and also the voltage drop from here to here. Okay, so you can form a KVL because you can close a loop across this current source for this mesh, for example. Okay, so let's assume Vx first, and we'll see why we don't have to use Vx. If you see something like this, you can directly ignore the process of assuming a Vx. Okay, so let's start from here. We're getting minus 40 volts plus 2 times I1 plus 8 times I1 minus I2 equals to 0. The second one, it's minus, it's not minus, it's 8 times I2 minus I1 plus 6 times I2. And here, you don't know the voltage, so I have to use Vx instead, right? And now when you are looking at the third mesh, the voltage the polarity you are seeing at first is the negative part of the Vx. So you have to do this for the first Vx and then plus 4 times I3, and then plus 20 volts equal to 0. And when you're looking at the three equations, it's very obviously, which is you have a plus Vx here and minus Vx here. So why not just directly combine these two equations? So you can get Vx cancel, and you do not have to list three equations. So you can directly list two instead. And but no matter if you combine them or not combine them, you are having three variables if you combine them, but you only have two equations. Okay, or four variables but three equations. So you are not able to solve all the variables. So which one is missing here? The 2 amps, because you haven't involved the 2 amp current source in anywhere. So you are missing information for the circuit. So 2 amp is the current going up, and you can see I3 is going up as well, and I2 is going down. So actually I3 minus I2 is the effective current flows through this wire, which is exactly 2 amps. So now you have all the equations for all the variables. But only one thing is you can simplify this part. If you add left to left, right to right, and you are going to get an equation looks like this. So nothing is changed, but only cancel VL, right? Vx is gone, then directly jump to here, equals to 0. Okay, so now you have 1, 2, 3 equations. So you can solve this problem easily. So in the future, if you see a current source bridging these two nodes, you can directly ignore it, and without assuming this guy, you can directly just imagine this is something like this. Just remove it. Very simple. That's called super mesh. But you still have to assume three currents. I1. Whenever you are doing a KVL over here, you directly do it in this loop instead of two individual loops. So let's see how we can do it. So no difference over here. So this is 8 ohms, 6 ohms, this is 4 ohms, it's 20 volts. How can do that? Start from here. That's minus A, not minus, just making this mistake again. So it's I2 minus I1. That's for this guy. And then plus 6 I2. And then here, right now, you have I3. Be careful. So if you do this, there's no difference as this method. If you compare these two equations, it's the same. Okay, so that's a super mesh method you need to know. There might be some chances you are going to see a super mesh problem with dependent source or dependent sources. So I will just show you the very last example of this lecture, and I'm not going to solve it, but I will just let you know all the possibilities you may see in the future in real life. So this is relatively slightly difficult problem. So see all these dependent sources with different values. So this is 193 volts. This is 4 ohms. This is 2.5 ohms. This is 2 ohms. And plus minus, this is called V delta, and this is 0.8 V theta, and this is 8 ohms, this is 7.5 ohms, this is 6 ohms, and the current of this guy is 0.4 V delta, which is, so this is a dependent current source. And you can see it's controlled by a voltage over here. So this is called voltage controlled current source. And this is 0.5 amps. It's a regular current source. And this guy is called voltage controlled voltage source. And so where's V theta? V theta is over here. And I think that's all these parameters we have for this circuit. So still the same, just use the match current method to list all the equations. So for the first one, it is minus 193 volts plus 4I1. And I mean, feel free to use super mesh because you have two current sources bridging these two nodes. So I'm going to directly ignore it. So just ignore it. So you actually only have one big mesh. So just keep going. This guy, which is 2.5 times I2, and then this guy, 2 times I what? I3. And plus this one, which is 0.8 as a voltage source, V theta. And coming back, A, I3, 7.5, I2, and 6I1 equals to 0. That's the first equation. That's a huge mesh. Okay, what about the second equation? You have to have all these dependent sources involved, right? So let's do it from the left to right. So let's look at the first one. That's 0.4 V delta. That's even though it's a V, but actually this is a current source, so it should be a current. So this current equals to, it's going up, so it equals to I2 minus I1. And the second one over here, no, this one. So V theta equals to what? You have I2 flowing that direction, so it should be minus I2 times 7.5 ohms. Okay. And let's see if there's anything else. V delta. So V delta equals to I3 times 2 ohms. Okay. Anything else? We haven't used this guy yet, right? So this is going to give us a relationship between I3 and I2. So I3 is going up. I3 minus I2 equals to 0.5 amps. And I think these are all these equations you need to solve it. Use all the i's to substitute the V delta and V theta in the circuit, so you can reduce the variables for all the V's, so you can only have all the currents over here, and then separate the coefficient, get the coefficient matrix for MATLAB and solve it. Use the method we covered. And that's everything I'm going to introduce in here. And this is all the examples you need to see. And I'm going to see you in the next lecture.